What if the universe isn't playing by the rules we think it does? For over 100 years, Einstein's theory of general relativity has been the backbone of our understanding of gravity, shaping everything from how we study black holes to the very expansion of the cosmos itself. But what if this cornerstone of physics isn't as unshakable as we've been led to believe? Even Einstein himself wrestled with doubts about his equations, scribbling in the margins of his notes, questioning whether the universe might hold secrets his math couldn't capture. And now, a new generation of physicists is picking up where he left off, daring to ask the questions that could unravel everything we thought we knew. Imagine standing at the edge of a black hole where time slows to a crawl and space bends like taffy. According to general relativity, this is the reality we're living in, a universe governed by the warping of space-time. But what if space-time isn't the final answer? What if gravity isn't a force at all, but something far stranger? Across the globe, scientists are exploring 22 radical concepts that challenge Einstein's legacy, ideas so bold they could rewrite the textbooks. From theories that suggest gravity might leak into other dimensions to the mind-bending possibility that dark energy is tearing the fabric of reality apart, these aren't just thought experiments. They're the cutting edge of physics, the clues that might finally unlock the universe's deepest mysteries. This isn't just about equations on a chalkboard. It's about the very nature of reality. If even one of these 22 ideas holds water, the implications are staggering. Black holes might not be what we think they are. The Big Bang could have a completely different origin story, and the fate of the cosmos that might be up for grabs too. So buckle up, because we're about to dive into the wildest, most controversial ideas in modern physics, the concepts that could shatter Einstein's framework and send us hurtling toward a new understanding of the universe. And it all starts with a question that's as simple as it is profound. What if space-time itself is an illusion? Einstein built his theory of relativity on one unshakable foundation. The speed of light in a vacuum is constant, an eternal cosmic speed limit etched into the fabric of physics. But what if that's not entirely true? Some physicists are daring to suggest that light's speed might have been different in the early universe, or even that it could fluctuate in ways we haven't yet detected. Picture a highway where the speed limit changes depending on when and where you're driving. That's the radical idea behind variable speed of light theories. Joe Megiddo, a physicist at Imperial College London, has spent years challenging Einstein's assumption, proposing that light may have traveled faster in the universe's infancy, helping to solve long-standing puzzles like why distant regions of space appear so uniform. This isn't just wild speculation. Tiny anomalies in cosmic measurements, like slight discrepancies in the afterglow of the Big Bang, hint that something might be off. If light speed isn't fixed, it would send shockwaves through physics, forcing us to rewrite the equations that describe everything from black holes to the expansion of space. Even more mind-bending, if light speed can change, then time itself might not be the steady, unchanging river Einstein envisioned. It could be more like a twisting, unpredictable current, bending in ways we're only beginning to understand. So where does that leave relativity? Still standing for now, but these cracks in its foundation are impossible to ignore. And if light speed isn't the constant we thought, what other so-called constants might be up for debate? This brings us to an even deeper question. Is time itself as rigid as relativity claims, or could it too be far more fluid than we ever imagined? If time is the ticking clock that keeps our universe in motion, What happens when the clock itself starts to dissolve? One of the most radical challenges to Einstein's framework comes from the idea that time might not be a fundamental part of reality at all, but rather an illusion, a side effect of something far more basic. Think of temperature. We experience it every day, but zoom in close enough and it vanishes, replaced by the chaotic dance of atoms. In the same way, some physicists argue time could be an emergent property, bubbling up from the quantum soup of the universe. Carlo Rovelli, a pioneer in loop quantum gravity, has spent decades exploring this mind-bending possibility. In his view, at the tiniest scales smaller than atoms, smaller than anything we've ever measured, time simply doesn't exist. The equations of quantum gravity work perfectly well without it, as if the universe at its core is timeless. This clashes violently with Einstein's vision, where time and space are woven together into an unbreakable fabric. Relativity treats time as a strict, unyielding dimension, the fourth thread in spacetime's tapestry. But if Rovelli and others are right, that tapestry might unravel when we look too closely. Imagine watching a movie where the frames suddenly stop flowing in order, scenes jumping backward and forward at random. That's the kind of reality loop quantum gravity hints at, a world where cause and effect don't follow neat, linear rules. If time emerges from quantum interactions, does that mean the past, present, and future are all equally real, just waiting to be stitched together by our perception? And here's where things get even stranger. If time isn't fundamental, how do we explain gravity's grip on the cosmos? Einstein's equations rely on time as a steady anchor, the rhythm that keeps planets orbiting and black holes spinning. But in a timeless quantum world, gravity might need a complete rewrite. Could it be that what we call gravity is just another emergent phenomenon, a shadow cast by deeper, invisible processes? The implications are dizzying. Without time as we know it, the very idea of before and after collapses, and with it, our understanding of how the universe evolves. So where does that leave us, staring into a quantum abyss where the most basic building blocks of reality defy intuition? If time is fluid, if it can vanish at the smallest scales, then perhaps the next great revolution in physics won't come from tweaking Einstein's equations, but from tearing up the rulebook entirely. And that leads us to an even more unsettling question. What if gravity itself isn't the dominant force we've always believed it to be? What if, like time, it's just a fleeting echo of something far more profound? What if dark matter doesn't exist at all? For decades, physicists have clung to the idea that invisible, mysterious particles must be lurking in the cosmos, explaining why galaxies rotate faster than Einstein's equations predict. But what if we've been chasing a shadow? Enter modified Newtonian dynamics, or MOND, a radical rewrite of gravity's rules that dares to ask, what if we're not missing matter, but misunderstanding the force itself? At the heart of MOND is a simple yet audacious idea. Instead of invoking dark matter to balance the cosmic books, it tweaks gravity's behavior at extremely low accelerations, like those found in the outskirts of galaxies. Imagine gravity as a rubber band. In our solar system, where accelerations are high, it snaps back predictably, obeying Newton's laws. But in the faint pull of a galaxy's outer edges, MOND suggests that rubber band stretches differently, bending the rules just enough to match what we observe. And here's the kicker, it works. MOND has an uncanny knack for predicting the rotation curves of galaxies without a single dark matter particle. Take the famous bullet cluster, often hailed as proof of dark matter's existence. Even here, MOND defenders argue their model holds up, tweaking gravity's math to fit the data, but it's not all smooth sailing. When scaled up to the universe at large, like the cosmic web of galaxy clusters, MOND stumbles. The same adjustments that perfectly predict galactic rotations fail to explain the larger structures we see. Critics like physicist Sabine Hossenfelder dismiss it as a patchwork fix, a clever but ultimately incomplete workaround that can't replace dark matter's sweeping explanatory power. Yet the debate rages on. Could man be pointing to a deeper truth, one where gravity itself isn't the immutable force we've always believed? If gravity's strength can change depending on where you are in the universe, what does that say about the laws we consider fundamental? This isn't just about swapping one theory for another. It's about questioning whether gravity, like time, might be something far more fluid than Einstein ever imagined. And if gravity isn't the steady, universal hand we thought, what other certainties might be up for grabs? So where does that leave us, staring at a crossroads where the very fabric of physics might need unraveling? If MOND is even partially right, it could mean that dark matter is a cosmic mirage, and that gravity, the force we've built our understanding of the universe upon, is playing by rules we're only beginning to decipher. But here's the real mind bender. What if gravity isn't even a force at all? What if, like time, it's just an echo of something deeper, a shadow cast by a reality we can't yet see? What if gravity isn't a force at all, but something far stranger, a cosmic side effect, a trick of the universe's information? That's the radical idea behind Eric Verland's entropic gravity, a theory that turns Einstein's framework on its head. Instead of gravity being a fundamental force woven into space-time, Verland proposes it emerges from entropy, the natural tendency of systems to become more disordered over time, like heat spreading through a room or ink dispersing in water. Imagine the universe as an unimaginably vast hologram, where every bit of matter and energy is encoded on its surface. In this view, gravity isn't pulling objects together. It's the universe's way of shuffling information, a statistical tendency for order to dissolve into chaos. Think of a crowded dance floor. As people move, they naturally spread out to avoid collisions, creating a kind of emergent force that wasn't there to begin with. Verland's math suggests gravity works the same way, a byproduct of microscopic quantum interactions we can't yet see. It's as if the cosmos is a cosmic hard drive, and gravity is just the system reorganizing its data. This isn't just poetic speculation. Verland's equations reproduce Newton's law of gravitation and even tweak Einstein's relativity, all without invoking gravity as a fundamental force. But here's the catch: can we test it? Critics argue entropic gravity is more philosophy than physics, a beautiful idea that's frustratingly hard to pin down. Unlike dark matter or modified gravity, Verland's theory doesn't yet make clear, unique predictions that telescopes or particle colliders could confirm. Supporters counter that subtle anomalies in galaxy rotations, places where gravity behaves unexpectedly, might already be hinting at entropy's hidden hand. The debate rages on, with some calling it a revolutionary leap and others dismissing it as a dead end, yet the implications are staggering. If gravity is just information settling into equilibrium, what does that say about the nature of reality itself? Are black holes not gravitational monsters but maximum entropy states, the universe's ultimate filing cabinets? And if spacetime isn't fundamental, could it be built from something deeper, an invisible lattice of quantum bits we've yet to uncover? Verland's vision blurs the line between force and illusion, suggesting that the fabric of the cosmos might be more like a cosmic mirage, shimmering into existence from something far more profound. What if the universe isn't just governed by physics, but by something resembling a cosmic computer program? That's the startling premise behind the idea that spacetime itself might be nothing more than a vast, shimmering network of quantum bits, a kind of celestial code running the simulation we call reality. Leonard Susskind, one of the architects of string theory, has spent years exploring this mind-bending concept known as the holographic principle. Picture the cosmos as a two-dimensional surface, like the screen of your phone, with all the richness of three-dimensional space. The stars, the galaxies, even you encoded on its flat face. It's as if the universe is a projection, a hologram where every bit of information is stored on a distant, invisible boundary we can't see. But how could this possibly work? Think of it like a pixelated image. Zoom in close enough on a digital photo, and the smooth curves dissolve into tiny squares. In the same way, string theory suggests spacetime might have a fundamental pixel size, a smallest possible unit beyond which you can't divide reality any further. These pixels aren't made of matter or energy. They're bits of pure information, flickering like ones and zeros in the universe's grand processor. And just as a video game renders a vast, open world from lines of code, these quantum bits could be stitching together the fabric of reality itself. This raises a question that borders on philosophy. If spacetime is code, who or what wrote it? Some physicists argue there's no need for a programmer, that the universe might simply compute itself into existence through the interactions of these quantum bits. Others wonder if we're glimpsing the edge of a deeper truth, one where the laws of physics are just the operating system of something far more profound. Either way, the implications are staggering. Black holes, for instance, might not be cosmic vacuum cleaners but dense knots of information, their event horizons acting like cosmic hard drives storing the universe's data. And here's where things get even stranger. If spacetime is pixelated, what does that say about the smooth, continuous reality we experience every day? Could the glitches in our perception, like the way particles pop in and out of existence at quantum scales, be the universe's version of a buffering screen? The holographic principle blurs the line between physics and metaphysics, suggesting that the solid, predictable world around us might be nothing more than a very convincing illusion. But if spacetime is a quantum code, where does it run? This is where the next radical idea comes into play, the possibility that our universe isn't the only one in the cosmic stack. Hidden dimensions folded into reality at scales too small to see could be the substrate where this code executes, the unseen architecture behind the scenes. If that's true, then the mysteries of gravity, dark matter, and even the nature of time itself might not be solvable in our three-dimensional slice of existence. The answers could be lurking in dimensions we've yet to uncover, waiting for the next revolution in physics to reveal them. Einstein's universe is a four-dimensional tapestry, three of space, one of time, woven together into the smooth fabric we call spacetime. But what if that fabric is just the visible edge of something far grander? String theory, one of the most ambitious frameworks in modern physics, throws open the door to a cosmos with not 4 but 10 or even 26 dimensions, hidden in folds too tiny for our instruments to detect. Picture an ant crawling along a telephone wire. From a distance, the wire looks like a simple one-dimensional line, but up close, the ant discovers a whole extra dimension, the wire's circular surface curled so tightly it's nearly invisible. That's the essence of Kaluza-Klein theory, an idea dating back to the 1920s that suggested gravity and electromagnetism could unify if we admitted just one extra compactified dimension. Fast forward a century, and string theory has taken this concept to dizzying new heights. Its equations demand these extra dimensions to make the math work, vibrating like the strings of a cosmic guitar to produce every particle and force we know. Some models, like brain-world scenarios, propose our entire universe might be a three-dimensional brain floating in a higher dimensional space, like a sheet of paper drifting in a vast, unseen ocean. In this picture, gravity could be the only force leaking into the bulk of these extra dimensions, explaining why it's so weak compared to electromagnetism or the nuclear forces. Imagine a flashlight shining on a wall. Most of its light stays on the surface, but a faint glow spills into the room. If gravity behaves like that faint glow, it might finally make sense why it's billions of times weaker than other forces. But here's the catch. Not a single shred of direct evidence confirms these extra dimensions exist. Particle colliders like the Large Hadron Collider have hunted for traces of them, tiny deviations in energy or microscopic black holes that would wink into existence if higher dimensions were real. So far, nothing. Critics argue this makes string theory less science and more mathematical poetry, a beautiful idea untethered from reality. Yet supporters counter that absence of proof isn't proof of absence. The scales we're talking about are 1 billion times smaller than anything we've ever probed. It's like trying to spot a single grain of sand on a beach from orbit. Our tools might just not be sharp enough yet. And then there's the black hole paradox. These cosmic monsters, long considered the ultimate test of general relativity, might hold clues to the higher dimensional puzzle. Some models suggest black holes could be portals to other dimensions, their singularities unraveling into hidden layers of reality. Others propose that what we perceive as a black hole's event horizon might actually be a shadow cast by gravitational interactions in a dimension we can't see. If true, it would mean even relativity's most iconic prediction is just a fragment of a far stranger truth. So where does this leave Einstein's four-dimensional masterpiece? Still standing, but maybe as a low-resolution snapshot of a much richer cosmos. If extra dimensions are real, they wouldn't demolish general relativity so much as swallow it whole, embedding it in a framework so vast it redefines the very meaning of space and time. And that raises an even more unsettling possibility. What if black holes aren't the end of the story, but the beginning? What if their crushing gravity is hiding not just singularities, but gateways to dimensions we've yet to imagine? At the edge of a black hole, physics reaches a breaking point where Einstein's serene vision of spacetime bends into a nightmare of contradictions. According to general relativity, crossing a black hole's event horizon should be uneventful, a smooth descent into oblivion. But quantum mechanics tells a far more violent story. Imagine stepping through what you think is a harmless threshold, only to find yourself vaporized by a blazing wall of energy, a firewall hotter than the core of a star. This isn't science fiction. It's the Firewall Paradox, a cosmic tug-of-war between relativity and quantum theory that's been raging since physicists Olmary, Marolf, Polchinski, and Sulker, known as the AMPS team, dropped their bombshell paper in 2012. Their math suggested that to preserve quantum mechanics' sacred principle of information conservation, black holes must annihilate anything crossing their horizons with an unforgiving inferno. But here's the problem. Einstein's equations insist that the event horizon is a place of no drama, where tidal forces are gentle enough to leave an astronaut blissfully unaware of their doom until it's too late. So who's right? The answer could rewrite our understanding of reality itself. Stephen Hawking, after decades of insisting black holes erase information, famously reversed course late in his career, conceding that quantum effects might indeed scramble information into a chaotic release of radiation, now called Hawking radiation. But even this didn't fully resolve the paradox. If firewalls exist, they'd shred the very fabric of spacetime continuity, turning black holes into cosmic kilns rather than the sleek, gravitational pits relativity predicts. Critics argue firewalls are a mathematical artifact, a sign that we're missing a deeper theory bridging quantum mechanics and gravity. Some propose wild alternatives, like black holes having fuzzy horizons where quantum fluctuations blur the boundary between inside and outside. Others suggest the firewall isn't a physical barrier but a holographic illusion, a trick of perspective from an observer outside the black hole. The debate is far from settled, but one thing's clear: if firewalls are real, they'd expose a fundamental flaw in Einstein's vision, proving that even black holes, relativity's crown jewels, can't escape the quantum revolution. This raises an even more unsettling question. What if the singularity at a black hole's core, the infinitely dense point where space-time supposedly crunches out of existence, isn't real at all? Could it be a mathematical mirage, a placeholder for our ignorance? Some theories propose that quantum effects prevent singularities from forming, replacing them with bizarre objects like fuzzballs or wormholes to other universes. If so, the very heart of a black hole might be stranger than anything Einstein ever dreamed. Einstein's equations famously predicted the existence of black holes, regions of spacetime where gravity becomes so intense that not even light can escape. But buried in those same equations was a nightmare: the singularity, a point of infinite density where the laws of physics break down completely. For decades, physicists accepted this as the grim fate of anything falling into a black hole, crushed into oblivion at the center. But what if singularities aren't real? What if they're just a sign that relativity, for all its brilliance, hits a wall when gravity becomes too extreme? That's where loop quantum gravity steps in, offering a radical alternative. Black holes might not end in singularities at all, but instead rebound in a cosmic bounce, like a rubber ball hitting the floor and springing back up. Picture a collapsing star. Under Einstein's rules, it would shrink endlessly, warping spacetime until it becomes infinitely small, a mathematical absurdity. Loop quantum gravity, however, suggests quantum effects kick in long before that point, creating a repulsive force so powerful it halts the collapse. Instead of a singularity, you'd get a dense knot of quantum spacetime that rebounds, spewing matter and energy back out. It's as if the black hole transforms into a white hole, a theoretical object that expels rather than absorbs. Carlo Rovelli and others working on this idea argue that the universe's quantum structure simply won't allow infinite densities. There's a smallest possible scale, a pixel of reality where spacetime can't be squeezed any further. This isn't just wild speculation. The math of loop quantum gravity naturally produces these bounces, offering a way to sidestep the singularity problem without invoking new physics. And it's not the first time someone's tried to dodge infinity. Einstein himself hated singularities, calling them a flaw in his equations. He spent years searching for ways to avoid them, convinced nature wouldn't permit such nonsensical extremes. In a way, loop quantum gravity picks up where he left off, armed with quantum tools he never had. But here's where it gets even more intriguing. If black holes can bounce, what does that say about the birth of our universe? Cosmologists have long struggled with the Big Bang singularity, the moment everything emerged from an infinitely dense point. But if loop quantum gravity is right, maybe the universe didn't begin with a bang at all. Maybe it's the rebound of a previous cosmos, a cycle of collapse and expansion stretching back further than time itself. This idea, known as the Big Bounce, turns the Big Bang from a one-time event into a single heartbeat in an eternal cosmic rhythm. The implications are staggering. If singularities vanish, so does the end point of black holes, and perhaps the starting point of the universe. Relativity's most extreme predictions would give way to a quantum-corrected cosmos, where gravity's fiercest grip is just a prelude to rebirth. It's a vision that would have thrilled Einstein, who once wrote, "The eternal mystery of the world is its comprehensibility." But if the universe really bounces, avoids singularities, and cycles endlessly, maybe the mystery runs even deeper than he imagined. And that leads us to an even more profound question. If black holes and the Big Bang aren't singularities, what other extremes might we have gotten wrong? Could the very fabric of space-time be hiding a quantum structure we've only begun to glimpse? The Big Bang has long been the reigning origin story of our universe, a fiery explosion from an infinitely dense point that birthed space, time, and everything we know. But what if that explosive beginning wasn't the start at all? What if it was just the latest chapter in an endless cosmic cycle, a rebound from a previous universe that collapsed before ours was born? This is the heart of bouncing cosmology, a radical reimagining of the universe's birth that sidesteps the singularity problem haunting Einstein's equations. Instead of a one-time eruption from nothingness, the Big Bang becomes a big bounce, a moment where a prior universe's death gave way to our own rebirth. The idea isn't entirely new. Even Einstein toyed with the notion of an oscillating universe, though he lacked the quantum tools to make it stick. Today, physicists like Roger Penrose have revived the concept with a twist. His conformal cyclic cosmology proposes that the universe doesn't just bounce, it resets. In this model, the distant future of our expanding cosmos, where all matter has dissolved into radiation, becomes mathematically identical to the ultra-smooth, ultra-hot state of the Big Bang. Time loses meaning at these extremes, allowing the end of one universe to seamlessly morph into the beginning of another. It's as if the universe is a phoenix, perpetually rising from its own ashes. Penrose even claims to have found evidence, faint circular patterns in the cosmic microwave background, the afterglow of the Big Bang, which he argues are gravitational echoes of black holes from a prior universe. These Hawking points, named for his late collaborator Stephen Hawking, are hotly debated. Critics dismiss them as statistical flukes, while supporters see them as tantalizing hints of a deeper cosmic rhythm. But bouncing cosmology isn't just about avoiding singularities, it's about rethinking gravity's role in the universe's evolution. If the Big Bang was a bounce, then Einstein's equations might need a quantum overhaul to describe what happens when spacetime gets squeezed beyond recognition. Loop quantum gravity, for instance, suggests that quantum effects create a repulsive force strong enough to halt collapse and trigger rebirth, like a trampoline flinging the universe back into existence. Yet there's a looming challenge to this elegant vision: dark energy. The mysterious force accelerating the universe's expansion could be the wrench in the gears of any cyclical model. If dark energy keeps pushing galaxies apart forever, the universe might end not in a crunch but in a cold, lonely fade-out, no bounce, no rebirth. Some theorists argue that dark energy's strength could change over time, leaving the door open for a future collapse. Others see it as proof that Einstein's cosmological constant, a number he once called his biggest blunder, might need another revision. This isn't just academic speculation. The fate of the cosmos hangs in the balance. Will it collapse and bounce back, or expand into oblivion? The answer could hinge on whether dark energy is a constant force or a shifting one, and whether Einstein's equations, which have guided us for a century, can adapt to a universe far stranger than he ever imagined. If they can't, then the next great revolution in physics might not come from tweaking relativity, but from tearing it down and starting anew. And that raises an even deeper question. What if dark energy isn't just a puzzle to solve, but a sign that gravity itself is changing over time? Dark energy might be the universe's most unsettling whisper, a force so baffling it could signal the end of Einstein's reign over cosmic physics. Discovered in the late 1990s when astronomers found the expansion of the universe wasn't slowing down as relativity predicted but speeding up, dark energy has since become the elephant in the room of modern cosmology. It makes up nearly 70% of the universe's energy budget, yet we have no idea what it actually is. Einstein's equations can accommodate it mathematically, his infamous cosmological constant, a fudge factor he once discarded as his greatest blunder, but that doesn't mean they explain it. What if dark energy isn't just a placeholder for our ignorance, but a glaring clue that relativity stumbles when confronted with the vast emptiness of intergalactic space? Enter quintessence, a theory that swaps the static cosmological constant for a dynamic, evolving field that permeates the cosmos. Picture dark energy not as a fixed feature of space-time, but as a kind of cosmic weather, shifting in strength over time like wind across a desert. Some models suggest quintessence could have been stronger in the early universe, weaker during the era of galaxy formation, and now surging again to drive accelerated expansion. Unlike Einstein's constant, which plods along unchanging, quintessence breathes, a living, fluctuating entity that might someday fade or even reverse, pulling the universe back into collapse. The implications are staggering. If true, the fate of the cosmos wouldn't be written in stone, but hanging on the whims of an invisible, evolving force. But quintessence isn't the only challenger. Vacuum metamorphosis proposes an even wilder idea, that dark energy isn't a force at all, but a phase transition in the fabric of spacetime itself. Think of water freezing into ice. At a critical threshold, its properties change abruptly. Similarly, as the universe expands and cools, vacuum metamorphosis suggests spacetime might undergo a sudden shift, flipping dark energy on like a cosmic switch. This would mean the acceleration we observe isn't due to some mysterious energy, but a fundamental change in how gravity operates at the largest scales. It's as if the rules of the universe quietly rewrote themselves billions of years ago, and we're only now noticing the effects. Yet for all their creativity, these theories share a common thread. They expose the cracks in relativity's armor. Einstein's equations work flawlessly from the scale of falling apples to the orbits of planets, but when applied to the universe as a whole, they require either a fudge factor or a complete overhaul. And here's where the plot thickens. Quantum mechanics, our other gold standard theory, paints dark energy in an equally confusing light. Quantum field theory predicts that empty space should teem with vacuum energy, a seething foam of virtual particles popping in and out of existence. But when physicists calculate how much energy this quantum froth should contribute to the cosmos, the number is off by a factor of 1 followed by 120 zeros, a discrepancy so colossal it's been called the worst prediction in the history of science. This isn't just a minor accounting error, it's a screaming paradox that pits relativity against quantum mechanics in a battle for the soul of physics. Either we're missing something fundamental about how gravity interacts with the quantum world, or one or both of these theories is profoundly incomplete. Some researchers argue dark energy is the smoking gun, proof that Einstein's equations break down when stretched across billions of light years. Others see it as a bridge, a phenomenon that might finally force us to unify relativity and quantum mechanics into a single, deeper framework. The stakes couldn't be higher. If dark energy is indeed a sign of relativity's limits, it would mean that the theory guiding our understanding of the cosmos for over a century is, at best, a local approximation, a brilliant but flawed map that fails at the edges of the known universe. And if that's true, what other surprises might be lurking in the darkness, waiting to rewrite the rules we thought we knew? Einstein's theory of general relativity paints gravity as the elegant bending of spacetime, a cosmic stage where planets, stars, and galaxies perform their celestial dance. But zoom into the quantum realm, and the stage itself dissolves into chaos, a seething foam of particles popping in and out of existence, defying the smooth, deterministic rules of relativity. This clash isn't just a minor disagreement, it's a full-blown crisis at the heart of modern physics. Unifying these two titans, relativity and quantum mechanics, has become the field's holy grail, a puzzle so profound its solution could rewrite our understanding of reality itself. Take black holes, for example. Relativity describes them as perfect vacuum cleaners, swallowing everything past their event horizons without a trace. But quantum mechanics insists information can never be truly destroyed. When these two ideas collide, contradictions erupt. Stephen Hawking's work showed black holes slowly evaporate, leaking radiation over eons. But where does the information go? Does it vanish, violating quantum laws, or linger somehow, defying relativity's predictions? This paradox isn't just academic, it's a glaring sign that Einstein's framework might crack under quantum pressure. So how do we bridge the gap? One approach, string theory, reimagines particles as tiny vibrating strings, their harmonies generating all forces, including gravity, in a universe with 10 or more dimensions. It's a beautiful idea, but critics argue it's more math than physics, lacking experimental proof. Then there's asymptotically safe gravity, a daring proposal that gravity's strength changes at different energy scales, becoming safe from infinities at the quantum level. Picture a river that smooths out its own rapids as you approach its source, a self-correcting theory where gravity's quantum flaws vanish naturally. But perhaps the most tantalizing clue lies in quantum entanglement, the eerie phenomenon where particles instantly influence each other across vast distances, seemingly faster than light. Einstein famously called this spooky action at a distance, a direct challenge to relativity's cosmic speed limit. Yet experiments confirm entanglement is real, leaving us with a haunting question. Does quantum weirdness break relativity's rules, or is space-time itself more flexible than Einstein imagined? Could entanglement be a hint that the universe connects through hidden layers, dimensions, or threads that relativity can't see? The search for quantum gravity isn't just about fixing equations. It's about uncovering whether space-time is fundamental or emergent, whether black holes are cosmic dead ends or portals, and whether the universe operates by rules we've yet to dream of. Every failure to reconcile these theories isn't a setback. It's a signpost pointing beyond Einstein's universe toward something far stranger. And if quantum gravity's missing link is found, it won't just complete physics, it might shatter our deepest assumptions about how reality works. Einstein called it spooky action at a distance, a phrase that perfectly captures the unnerving strangeness of quantum entanglement. Picture two particles born from the same quantum event, separated by billions of light years, yet still mysteriously linked. Change the spin of one and the other instantly flips to match, as if space and time between them don't exist. This isn't just a theoretical curiosity, it's been proven in labs again and again, with particles responding faster than light could ever travel between them. And that's the problem. Relativity insists nothing can outpace light's cosmic speed limit, yet entanglement shreds that rule without hesitation. Here's where things get even weirder. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a radical solution. What if entanglement isn't breaking relativity's rules but secretly obeying them through hidden tunnels in spacetime? They dubbed this idea ER equals EPR, merging two of Einstein's most famous concepts. The ER refers to Einstein-Rosen bridges, better known as wormholes, the hypothetical shortcuts through spacetime predicted by general relativity. The EPR nods to the Einstein-Podolsky-Rosen paradox, the thought experiment that first exposed entanglement's spooky connections. The theory suggests that entangled particles might be connected by microscopic wormholes, threading through higher dimensions we can't see. It's as if the universe, faced with relativity's speed limit, cheats by folding space-time itself to keep these particles in touch. Think of it like a cosmic game of telephone. Normally, sending a message across the universe would take billions of years at light speed. But if space is secretly pleated like an accordion, with wormholes stitching distant points together, information could hop through unseen shortcuts, no speed limit violation required. This would mean entanglement isn't magic, it's geometry. The particles aren't communicating faster than light. They're just taking a hidden back road relativity didn't account for. But are these wormholes real or just mathematical sleight of hand? The math checks out. Einstein's equations do permit wormholes, though they'd require exotic matter with negative energy to stay open, something we've never observed. Critics argue this makes the whole idea speculative, a clever metaphor without physical substance. Supporters counter that black holes were once considered mathematical oddities too, until we found them peppering the cosmos. If wormholes exist, even on quantum scales, they'd offer a breathtaking resolution to the conflict between relativity and quantum mechanics. Two theories seemingly at war, secretly describing the same phenomenon from different angles. And that raises an electrifying possibility. If entanglement and wormholes are two sides of the same coin, could we someday manipulate one to control the other? Imagine engineering entangled particles to stabilize a wormhole, turning a fleeting quantum link into a traversable gateway. It sounds like science fiction, but the equations hint it might not be impossible. The catch: any attempt to send information through such a wormhole would likely destroy the entanglement, collapsing the tunnel like a soap bubble. Nature, it seems, guards its shortcuts carefully. Yet the implications ripple far beyond lab experiments. If space-time is threaded with these invisible quantum connections, the universe might be far more interconnected than we ever dreamed. Galaxies on opposite sides of the cosmos could harbor particles whispering to each other through hidden wormholes, weaving a cosmic web entanglement built long before stars began to shine. This isn't just about fixing physics, it's about uncovering a universe where distance is an illusion, and the fabric of reality is stitched together by threads we're only beginning to grasp. Which brings us to the next puzzle. If wormholes are relativity's loopholes, could they be stable enough to traverse, or are they doomed to snap shut, leaving us with only quantum hints of their existence? The answer might lie in the very nature of spacetime itself, and whether it's as unbreakable as Einstein believed, or far more fragile than we ever imagined. Wormholes aren't just science fiction, they're lurking in Einstein's equations, hidden tunnels through spacetime that could connect distant corners of the universe in an instant. The math is clear. If you could thread a wormhole with something called exotic matter, a hypothetical substance with negative energy, it might stay open long enough to step through. Picture a crumpled piece of paper with two dots on opposite sides. Fold the paper, punch a hole through both dots, and suddenly the journey that once spanned the entire page takes just a single step. That's the dream of traversable wormholes, cosmic shortcuts that could make interstellar travel as routine as crossing the street. Kip Thorne, the Nobel laureate who inspired Interstellar's black hole visuals, laid the groundwork for this idea in the 1980s. His calculations showed that exotic matter could counteract a wormhole's natural tendency to collapse, acting like a scaffolding to hold the tunnel open. But here's the catch: exotic matter isn't just rare, it might not exist at all. Quantum theory allows for fleeting bursts of negative energy, like the Casimir effect, where empty space pushes plates together. But sustaining enough to stabilize a wormhole, that's like trying to build a bridge out of soap bubbles. And then there's the time travel problem. Thorne's work revealed something even wilder. a traversable wormhole could become a time machine. Imagine one end of the tunnel stays near Earth while the other rockets off at near light speed. Time slows for the moving end thanks to relativity, creating a clock discrepancy. Step through the wormhole years later, and you might emerge in Earth's past, not just another place but another when. Suddenly, you're face to face with paradoxes. What if you prevent your own birth? Or alter history in ways that erase the future that built the wormhole? Einstein's equations don't forbid this, but physics recoils at the chaos. The chronology protection conjecture, proposed by Stephen Hawking, suggests the universe might sabotage time travel before it happens, with quantum effects or gravitational feedback snapping wormholes shut. It's as if reality has a built-in immune system, rejecting temporal infections before they spread. Yet the fact that relativity even allows these scenarios forces us to ask, is time travel not just possible, but inevitable in some corner of the cosmos? And if so, does that mean time itself is more malleable or more fragile than Einstein ever guessed? The implications ripple far beyond wormholes. If space-time can be punctured and stitched into shortcuts, then causality, the bedrock of physics, might be negotiable. Events wouldn't need to follow neat, linear chains where causes always precede effects. The universe could become a tangled web of before and after with no clear direction, where the past is just another destination. For relativity, this isn't a minor tweak. It's an existential threat. The theory's elegant spacetime tapestry might unravel entirely if time loops are allowed, leaving us to wonder, are wormholes the key to unlocking the cosmos, or the trapdoor that sends physics tumbling into the unknown? Einstein's equations don't just permit time travel, they practically invite it. Hidden in the fabric of general relativity are bizarre solutions known as closed time-like curves, loops where spacetime bends back on itself so tightly that you could, in theory, travel into your own past. Picture a cosmic Möbius strip where every step forward along the curve eventually brings you back to where and when you started. It's the stuff of science fiction, like the time-warping planet in Interstellar, but the math is shockingly real. Kip Thorne and others have shown that with enough negative energy or a rapidly spinning cosmic string, these loops could exist, turning the universe into a labyrinth where cause and effect twist into knots. But here's where quantum mechanics slams on the brakes. Stephen Hawking, skeptical of the chaos time loops would unleash, proposed the chronology protection conjecture, a cosmic rule that forbids paradoxes by any means necessary. Imagine the universe as a meticulous editor, deleting any event that would create a logical inconsistency before it hits the presses. Hawking's idea suggests that quantum fluctuations near a budding time loop would escalate into a catastrophic feedback loop, like a microphone screeching when placed too close to a speaker. The resulting burst of energy would destroy the wormhole or collapse the curve before anyone could exploit it. In other words, physics might have a built-in undo button for time travel, preserving causality at all costs. Yet the debate is far from settled. Some theorists argue that quantum mechanics could allow time loops, but only in ways that avoid paradoxes entirely. Think of it like a choose-your-own-adventure book where every decision branches into a new timeline. Traveling back might spawn a parallel universe rather than rewrite history. Others propose that closed time-like curves aren't forbidden but encrypted, their secrets locked behind quantum firewalls or computational barriers we can't yet breach. It's as if the universe hides its time travel blueprints in plain sight, daring us to crack the code. This raises an even more unsettling possibility. If time loops exist but are quarantined by quantum rules, could reality itself be operating like a simulation? After all, what better way to prevent paradoxes than to run the cosmos on a cosmic processor with error correction protocols? the idea isn't as far-fetched as it sounds. Physicists like James Gates have discovered error-correcting codes, the same ones used in computer programming, embedded in the equations of string theory. It's as if the universe's source code contains its own debugging software, patching glitches before they crash the system. So where does that leave Einstein's time-twisting predictions? Still dazzling, but perhaps fenced off by quantum fine print, closed time-like curves might be less like highways to the past and more like museum exhibits behind glass, untouchable, reminders of what relativity allows but quantum law denies. Or worse, what if they're shadows of a deeper truth, hints that our reality is just one layer of a far stranger construct? The answer might depend on whether physics is a set of cosmic laws or lines of code waiting to be rewritten. What if the universe isn't just governed by physics but programmed by it? The simulation hypothesis, popularized by philosopher Nick Bostrom, throws open a radical possibility that our reality isn't the base layer of existence but an artificial construct, an advanced civilization's digital creation. In this view, the laws of physics Einstein's relativity included aren't fundamental truths but lines of code in a cosmic simulation, rendering black holes, wormholes, and even time itself as mere features of the software. Bostrom's trilemma lays out the chilling logic. Either civilizations never reach technological maturity, they choose not to run ancestor simulations, or we're almost certainly living in one. Given the staggering computational power a post-human society might wield, the third option starts to feel less like sci-fi and more like statistical inevitability. But here's the twist: if we're in a simulation, the glitches might already be visible. Quantum mechanics, with its particles that exist in multiple states until observed, behaves eerily like a video game rendering graphics only when a player looks. The Planck length, the smallest possible unit of space, could be the universe's pixel size, a telltale sign of a finite resolution. Even entanglement's spooky connections might make sense if the simulation shortcuts calculations by linking distant particles behind the scenes. The most unsettling clue: quantum gravity researchers keep stumbling onto hints that spacetime behaves like a network, with loop quantum gravity describing it as a fabric woven from tiny, discrete threads. It's as if we're peeling back reality's veneer and finding circuitry underneath. Critics dismiss the simulation argument as untestable metaphysics, a fun thought experiment with no way to falsify it. After all, how could a program detect its own programming? Yet some scientists aren't ready to concede. Proposals like simulation signatures suggest hunting for anomalies, energy constraints in high-speed particles that resemble processing limits or repeating patterns in cosmic rays that might reveal a lattice-like structure to spacetime. Others argue that if the simulators left an intentional Easter egg, a mathematical cipher in the constants of nature, we might crack it given enough time. The irony is delicious. Physics, the discipline built on empirical proof, now flirts with a theory that might forever elude it. But whether the simulation hypothesis holds water or not, it forces a profound question. If reality can be modeled so precisely that even its inhabitants doubt its authenticity, does it matter whether the universe is real or rendered? The equations work either way. And that blurring of boundaries between code and cosmos, between creator and creation, leads us to the next great math-driven mystery. If the universe can be described as information, what does that say about the nature of existence itself? Einstein's universe runs like clockwork, predictable, precise, with every coordinate in spacetime obeying the strict rules of geometry we learned in school. But what if those rules are just an approximation, a smoothed-over version of a far stranger truth? Elaine Con's, a towering figure in mathematics, proposes exactly that with his theory of non-commutative geometry, a framework where space-time coordinates don't follow the usual rules. Normally, if you tell someone to walk 5 steps east, then 5 steps north, they'll end up in the same spot as if they'd walked north first, then east. The order doesn't matter, but in Kahn's vision, the universe plays by different rules. X, Y doesn't equal YX. The sequence changes the outcome, as if space itself has a hidden friction, a quantum graininess that twists the path depending on how you move through it. Picture your GPS struggling in a dense city, its readings smearing as skyscrapers scatter the signals. Now imagine that fuzziness isn't a bug, it's the universe's true nature. At scales smaller than atoms, Kahn argues, space-time might not be a smooth grid but a chaotic mosaic where positions blur and directions tangle. This isn't just abstract math. If coordinates don't commute, the very fabric of reality becomes a dynamic, shifting thing more like a cloud of probabilities than Einstein's rigid stage. Quantum physics already hints at this. Heisenberg's uncertainty principle tells us we can't pin down a particle's position and momentum simultaneously. Non-commutative geometry takes that further, suggesting space-time itself resists being precisely mapped, its coordinates dancing just out of reach, and here's where it gets even wilder. If space-time is fundamentally fuzzy, what does that say about the nothingness of empty space? Einstein's relativity treats the vacuum as a passive backdrop, a static canvas waiting for matter to warp it. But Kahn's framework implies that even the void is alive with structure, buzzing with geometric activity too subtle for our instruments to detect. Think of it like static on an old TV screen, seemingly random noise, but under the surface, it's a crackling sea of potential. This aligns with quantum field theory, where the vacuum isn't empty at all, but a frothing soup of virtual particles flickering in and out of existence. The implications ripple through cosmology. If spacetime's coordinates don't commute, black holes might not have sharp event horizons but smeared boundaries, like a photograph with too much motion blur. The Big Bang singularity could dissolve into a quantum foam, its infinite density smoothed out by geometry's refusal to be pinned down. Even dark energy, the mysterious force accelerating the universe's expansion, might find an explanation here as the cumulative effect of spacetime's non-commutative jitter at cosmic scales. Critics argue this is mathematical poetry, untethered from experiment. Yet supporters point to subtle anomalies in high-energy physics and the behavior of spacetime near singularities, places where Einstein's equations break down, but Kahn's math might hold the key. Whether non-commutative geometry rewrites relativity or simply refines it, one thing is clear: the universe's GPS might be far less reliable than we thought. And if empty space isn't empty, what else have we been missing? Einstein's universe is a tapestry of smooth, unbroken spacetime, a cosmic stage where gravity bends the fabric with elegant precision. But dive down to the smallest scales imaginable, where distances shrink to a billionth of a meter, and that pristine fabric begins to boil. This is the realm of quantum foam, a concept dreamed up by physicist John Wheeler in the 1950s. Picture spacetime not as a calm pond but as a churning ocean, where virtual particles erupt into existence and vanish in an instant, their fleeting energy twisting the very geometry of reality. These aren't just tiny ripples, they're microscopic tempests, warping spacetime so violently that the idea of a smooth, continuous universe dissolves into chaos. Wheeler's foam isn't just poetic imagery. Quantum mechanics tells us that empty space is anything but empty. At these unimaginably small scales, particles and antiparticles borrow energy from the vacuum, dancing into existence for fractions of a second before annihilating each other. This isn't theoretical, it's been measured in labs with phenomena like the Casimir effect, where two metal plates placed incredibly close together feel a subtle push from these quantum fluctuations. But here's the catch: every time these particles flicker into being, they warp spacetime around them. Multiply that by the sheer number of virtual pairs popping in and out everywhere, and suddenly, relativity's smooth fabric looks more like a storm-tossed sea. This creates a glaring clash with Einstein's vision. General relativity assumes spacetime is continuous, a stage that bends but never fractures. But quantum foam suggests that at the tiniest scales, the stage itself is riddled with holes, tunnels, and bubbles, a frothing mess where concepts like here and now lose all meaning. It's as if the universe has a pixelated underbelly, a hidden layer where geometry itself stutters. Some theories, like loop quantum gravity, take this even further, proposing that spacetime isn't just foamy but made of discrete, indivisible chunks like atoms but for the fabric of reality. Yet the real shock comes when we calculate the energy of this quantum frenzy. If you add up all the fleeting energy of these virtual particles, the result is a number so absurdly large it defies comprehension: 10 to the power of 113 joules per cubic meter. That's enough energy in a coffee cup to obliterate the observable universe countless times over. Physicists call this the vacuum catastrophe, a discrepancy between prediction and reality so vast it's been called the worst failure of theoretical physics. Because here's the thing: when we look at the cosmos, we don't see this unimaginable energy. Space is eerily calm, its expansion driven by a far weaker force we call dark energy. So where does all that quantum foam energy go? Some argue it's cancelled out by negative energy fluctuations, a cosmic balancing act we don't yet understand. Others think it's proof that our theories are missing something fundamental, a hidden symmetry or a deeper layer of physics that reconciles the quantum frenzy with the universe's serene appearance. Either way, the quantum foam isn't just a curiosity. It's a screaming anomaly, a sign that relativity and quantum mechanics can't both be right in their current forms. And that raises an unsettling question. If spacetime is foamy at its core, what other illusions might we be mistaking for reality? Could even gravity itself be a side effect of this quantum chaos, a ripple on the surface of something far stranger? The vacuum of space isn't empty, it's a seething, writhing storm of quantum energy, a chaos so intense it threatens to tear apart the very foundation of physics. According to quantum field theory, every cubic centimeter of so-called empty space buzzes with virtual particles, pairs of matter and antimatter that flicker into existence for vanishingly brief moments before annihilating each other. These aren't just mathematical quirks. Their energy has been measured in labs, bending metal plates in the Casimir effect and leaving ghostly fingerprints on the cosmos. But here's the problem: when physicists calculate how much energy this quantum frenzy should contribute to the universe, the numbers spiral into absurdity. The theoretical prediction exceeds the observed strength of dark energy, the force accelerating cosmic expansion, by a factor of 1 followed by 120 zeros. It's the most staggering mismatch in science, a gulf so vast it's been dubbed the vacuum catastrophe. This isn't just a minor accounting error. If quantum field theory were right about the vacuum's energy, the universe should have ripped itself apart nanoseconds after the Big Bang. The fact that we exist at all suggests something's profoundly wrong with our understanding of empty space. Einstein's cosmological constant, originally introduced as a fudge factor to balance his equations, was resurrected to explain dark energy's gentle push on the cosmos. But the observed value is laughably tiny compared to the quantum vacuum's predicted fury, like balancing a feather on a mountain and calling it stable. The disconnect is so glaring that Nobel laureate Steven Weinberg called it the bone in the throat of theoretical physics. Desperate for solutions, some physicists have turned to radical alternatives. One compelling idea is that the vacuum's energy isn't missing. It's cancelled out by some hidden symmetry, a cosmic seesaw where positive and negative fluctuations balance perfectly. String theory hints at such mechanisms with its intricate webs of extra dimensions and supersymmetric particles, but after decades of searching, no evidence for these cancelling effects has emerged. Others propose a darker possibility, that our universe isn't finely tuned, but a statistical fluke in an infinite multiverse, where we just happen to occupy the one bubble where the numbers improbably align. It's an unsettling answer, more philosophical than physical, leaving many scientists cold. Then there's the nuclear option. What if gravity itself isn't fundamental? Eric Verland's Emergent gravity suggests that what we perceive as gravity might be a side effect of quantum entanglement and entropy, like heat emerging from the motion of atoms. In this view, dark energy and the vacuum catastrophe could be mirages, symptoms of our misunderstanding of spacetime's true nature. If gravity emerges from deeper quantum processes, its apparent weakness compared to other forces might simply reflect incomplete bookkeeping, a cosmic illusion created by ignoring the universe's hidden ledger. The vacuum energy paradox isn't just a puzzle, it's a blazing signal that our two greatest theories, quantum mechanics and general relativity, are missing a crucial handshake. Either an undiscovered principle harmonizes them, or one or both must fall. For now, the void keeps its secrets, whispering that the universe's true engine may lie not in the stars, but in the invisible quantum storms raging in the space between them. What if gravity isn't pulling us down at all, but projecting from somewhere else like a shadow cast by hidden data? Eric Verland's holographic gravity takes his earlier entropic ideas even further, proposing that the three-dimensional force we experience might be nothing more than a cosmic illusion, a hologram rendered from information stored on a two-dimensional surface at the edge of the universe. Think of it like a movie screen. The images appear to have depth, but every explosion, every soaring spaceship, is just patterns of light painted on a flat canvas. In this radical view, gravity isn't woven into space-time. It's a side effect, a statistical glimmer emerging from the universe's relentless drive toward disorder, like heat radiating from a bustling crowd. This isn't just poetic metaphor. The math echoes one of the most profound discoveries in theoretical physics, the anti-de Sitter/conformal field theory duality, or AD-S/CFT. Born from string theory, AD-S/CFT suggests that a higher dimensional universe with gravity like ours could be perfectly described by a lower dimensional world without it, where particles interact like ink on a surface. It's as if the cosmos is a cosmic optical trick, where the 3D world we perceive is just a projection of 2D data humming at the boundaries of reality. Black holes in this framework become extreme examples. Their immense gravitational pull might just be the universe's way of encoding unimaginable amounts of information onto their event horizons, like a hard drive compressing files to their limit. But here's where the holographic principle starts bending causality, a cornerstone of relativity, into knots. If gravity emerges from information processing, then cause and effect might not be the immutable chain Einstein envisioned. Picture a domino rally where the tiles fall before you knock them over, or a fire whose smoke appears before the match is struck. In a holographic universe where time and space are rendered from underlying data, the sequence of events could become fluid, reshuffled by the way information is processed at the fundamental level. Quantum experiments already hint at this, with particles seemingly deciding their states retroactively, as if the universe is buffering its own timeline. Critics argue this reduces physics to metaphysical speculation. How do you test a universe that might be running on cosmic code? Yet supporters point to black hole thermodynamics, where the entropy of a black hole scales precisely with its surface area, not its volume, as if the true stuff of reality is painted on its edges, not stuffed inside. And if that's true for black holes, why not for the cosmos itself? The implications are dizzying. Gravity, causality, even the passage of time might not be fundamental, but emergent phenomena, flickering into existence from a deeper, stranger layer of reality we've yet to decode. So where does that leave relativity's pristine spacetime? Still standing, but perhaps as a user interface, a convenient illusion masking the universe's true mechanics. And if gravity is a hologram, what other certainties might be up for negotiation? Could the laws we consider universal just be local ordinances, quirks of our particular corner of the cosmic projection? The answer might depend on whether we're players in the universe or lines in its source code. Einstein's universe runs like a flawless clock, every tick of time, every curve of space, meticulously governed by the unbreakable laws of causality. But what if spacetime isn't smooth and continuous at its core, but stitched together from countless tiny shards, each obeying its own microscopic rules? That's the radical premise of causal dynamical triangulations, a daring approach to quantum gravity that rebuilds the cosmos from the ground up. Picture a child assembling a mosaic from triangular tiles, where each piece must fit perfectly with its neighbors, edges aligned, angles precise. Now imagine those tiles aren't just shapes, they're fragments of spacetime itself, each carrying a sliver of causality, the unshakable rule that cause must always precede effect. This isn't just geometry for geometry's sake. By forcing spacetime to emerge from these causal building blocks, physicists like Renate Loll and Jan Amjorn have found a way to tame the chaos of quantum gravity. In their simulations, the universe starts as a soup of disconnected triangles, a quantum foam of possibilities. But as the rules of causality take hold, something remarkable happens. Order bubbles up from the chaos. The triangles begin to link in ways that respect the flow of time, gluing themselves into a smooth, four-dimensional structure that looks, at least from a distance, like the universe we recognize. It's as if reality is a vast origami project, folding itself into existence one causal crease at a time. The real magic lies in what this approach avoids. Unlike string theory's extra dimensions or loop quantum gravity's tangled networks, causal dynamical triangulations keep spacetime stubbornly four-dimensional, refusing to venture into unseen realms. Instead, it finds complexity in simplicity, letting causality sculpt the universe from humble ingredients. Think of it like a pixelated image. Up close, you see the jagged edges, but step back, and the picture resolves into something seamless. The equations even predict that at the tiniest scales, spacetime might have a fractal structure, a self-similar whirl of triangles within triangles, echoing infinitely downward. But how do we test such an abstract idea? Here's where the quantum meets the concrete. If spacetime is truly pixelated, those jagged edges might leave fingerprints in the light traveling across the cosmos. Ultra-high-energy gamma rays, for instance, could stumble over spacetime's granularity as they race toward Earth, arriving slightly delayed compared to lower-energy photons. Telescopes like the Fermi Gamma Ray Space Telescope have hunted for these delays, though the results remain tantalizingly inconclusive. Others propose that gravitational waves, ripples in spacetime itself, might carry whispers of this underlying structure, subtle distortions that reveal the universe's hidden geometry. The challenge is immense. Probing spacetime at these scales requires energies beyond anything our particle colliders can muster, realms where a single gram of matter would pack the energy of 1,000 suns. Yet the promise is irresistible, a theory that marries quantum mechanics and gravity without abandoning causality, Einstein's sacred thread, and that raises a thrilling possibility. If spacetime is built from causal fragments, then the arrow of time, the relentless march from past to future, might not be an emergent property, but baked into the universe's very blueprint. The triangles don't just build space, they encode time's flow, stitching causality into the fabric of reality itself. As we stand on the brink of testing these ideas, one thing is clear. Whether causal dynamical triangulation survives or falls, it's already reshaped the quest for quantum gravity. By treating causality not as a consequence but as a foundation, it offers a universe where time isn't an illusion but the glue that holds everything together. And that leads us to the final, most pressing question of all. If spacetime is a mosaic, who or what laid the first tile? For over a century, Einstein's theory of general relativity has stood firm against every experimental challenge until now. The first direct detection of gravitational waves by LIGO in 2015 was a triumph, confirming one of relativity's boldest predictions. Ripples in spacetime from colliding black holes over 1 billion light-years away stretched and squeezed Earth by less than 1,000th the width of a proton, yet LIGO lasers caught them. It was physics at its most elegant, Einstein's math, penned in 1915, perfectly describing events in a distant cosmos he'd never see. But beneath this success lies a growing unease. The same experiments that verify relativity are also exposing cracks in its foundation, revealing gaps where the theory stumbles, where the universe refuses to follow the script. Take dark matter, for instance. The Milky Way's rotation curves defy Newton and Einstein alike, spinning stars faster than their gravity should allow. For decades, physicists assumed invisible matter must be the culprit, yet after countless experiments hunting particles from underground labs to space telescopes, dark matter remains stubbornly invisible. Meanwhile, tabletop quantum experiments are probing gravity's behavior at microscopic scales, where relativity and quantum mechanics collide. In a lab in Vienna, scientists have suspended tiny glass beads in vacuum chambers, watching for signs that gravity behaves differently when mass is in quantum superposition both here and there simultaneously. If gravity responds to quantum weirdness in ways Einstein didn't predict, it could upend our understanding of how spacetime interacts with the quantum realm. Then there's the Hubble tension, a growing headache in cosmology. Measurements of the universe's expansion rate disagree by nearly 10% depending on whether we use distant supernova or the cosmic microwave background. It's as if the cosmos can't decide how fast it's growing, a discrepancy some theorists argue might require tweaking relativity itself. Even black holes, relativity's crown jewels, are causing trouble. The Event Horizon Telescope's image of M87's black hole matched Einstein's predictions beautifully, but smaller black holes exhibit quirks that don't fit. Some spin faster than relativity allows, while others emit X-rays in patterns that suggest spacetime near their horizons isn't warping as expected. This avalanche of anomalies has led some physicists to declare a theory crisis, a recognition that our foundational frameworks, while spectacularly successful, might be incomplete. The crisis isn't just about missing pieces. It's about the growing sense that relativity and quantum mechanics are two different languages describing the same reality, neither fully correct. Efforts to bridge them from string theory to loop quantum gravity remain untested, leaving the field in a precarious limbo. As Nobel laureate Roger Penrose put it, we're in a period where the next big revolution could come from anywhere or nowhere. Amid this uncertainty, the most speculative ideas are gaining traction. Some theorists are revisiting discarded alternatives like Brand's-Dick theory, which tweaks gravity's strength across space. Others are probing whether the universe's constants, the speed of light, the strength of gravity, might drift over cosmic time. And then there's the wildest frontier of all, experiments attempting to manipulate gravity itself. Projects like the Fermilab holometer hunt for spacetime's hypothetical pixelation, while quantum physicists in Chicago are entangling diamonds to test if gravity can behave like a quantum force. These aren't just fringe ideas, they're desperate measures for desperate times, a recognition that the universe's deepest secrets might lie outside the boundaries of our current theories. The irony is palpable. The same tools that confirmed relativity's brilliance, LIGO lasers, Hubble's gaze, quantum labs, are now the ones hinting at its limits. Whether these anomalies lead to a grand new synthesis or deeper confusion remains unclear, but one thing is certain: the next revolution in physics won't come from polishing old equations. It'll emerge from the chaos of the unexplained, from the experiments that break rather than confirm. And when it arrives, Einstein's masterpiece might not be overturned but transcended, its truths revealed as fragments of a far stranger reality. What if reality itself bends to the gaze of the observer? At the furthest edge of physics, where equations blur into philosophy, lies a notion so radical it redefines the act of seeing, the idea that consciousness might not merely perceive the universe but actively shape it. This is the participatory universe hypothesis, a fringe theory that stitches together quantum mechanics' strangest quirks with age-old questions about the nature of existence. In quantum experiments, particles exist in hazy superpositions until measured electrons spinning both clockwise and counterclockwise, photons acting as waves and particles simultaneously. The moment an observer intervenes, this quantum fog collapses into a definite state. Extend this principle to the cosmos, and you get a breathtaking possibility. Space-time itself might be a collaborative artwork, its structure crystallizing under the weight of conscious observation. The roots of this idea trace back to physicist John Wheeler, who envisioned the universe as a self-excited circuit where observers, humans, animals, even hypothetical alien civilizations, retroactively define reality through their questions. Picture a cosmic game of 20 questions where the answers don't just reveal the world but create it. Wheeler's delayed choice experiments hammered this point home. Photons seemed to decide whether they behaved as particles or waves based on measurements made after they'd already traveled their path, as if the present were rewriting the past. It's as though the universe is an unscripted play, its plot unfolding only when the audience looks. Critics, and they are legion, dismiss this as metaphysical overreach. The vast majority of physicists argue that observation in quantum mechanics refers to interactions with any system. A stray photon or a dust grain counts as much as a human mind. They point out that stars and galaxies existed for billions of years before life emerged. If consciousness creates reality, who was there to observe the Big Bang? Yet supporters counter with a provocative twist. What if consciousness isn't limited to brains, but is a fundamental property of the universe like mass or charge? In this view, the cosmos might be more like a vast neural network, with every quantum event a flicker of proto-awareness stitching reality together. The implications are dizzying. If observation molds space-time, then black holes where observation breaks down might be zones where reality frays at the edges. The Big Bang could resemble a quantum fluctuation magnified by its own observation, like a tree falling in a forest where the forest itself is the listener. Even dark energy's acceleration might take on new meaning. not as a force, but as the universe's response to the growing complexity of its observers, a cosmic canvas stretching to accommodate ever deeper layers of perception. Mainstream science remains deeply skeptical, and for good reason. There's no mechanism, no equations, no way to test whether consciousness holds such power. But the theory's allure persists, not least because it mirrors ancient intuitions. From Hindu cosmology's dreaming Vishnu to Berkeley's idealism, humans have long wondered if reality is a shared hallucination. Modern physics, in its quest to unify quantum weirdness with cosmic structure, keeps stumbling into similar territory, as if the universe is hinting that the line between observer and observed might be the ultimate illusion. As we stand at the edge of this speculative frontier, one thing becomes clear: whether consciousness shapes space-time or not, the act of questioning reality has already reshaped us. Every paradox, every anomaly, every crack in Einstein's framework isn't just a puzzle to solve. It's an invitation to reimagine our place in the cosmos. And that, perhaps, is the most radical idea of all, that the universe's greatest mysteries might not be out there in the void, but woven into the very fabric of how we perceive, measure, and dream. From the churning quantum foam beneath spacetime's surface to the holographic whispers of a universe encoded on its boundaries, these 22 radical concepts don't just challenge Einstein's general relativity, they stretch it to the breaking point. Each idea, whether it's gravity emerging from entropy or time dissolving into illusion, exposes a crack in the foundation of our cosmic understanding. Black holes might not be the perfect vacuums relativity predicts, but fuzzballs or wormholes. Dark energy could be a phase transition in the vacuum itself, not a fixed constant. Even causality, the unshakable rule that cause must precede effect, wobbles under the weight of closed time-like curves and quantum entanglement's spooky connections. Yet this isn't a crisis, it's science at its most exhilarating. Every great theory in history, from Newton's clockwork cosmos to Einstein's warped spacetime, has faced moments where the data outran the math. And every time, the solution wasn't to cling tighter to old ideas, but to let them evolve or even collapse under the weight of something new. The cracks in relativity aren't signs of failure, they're portals. They're invitations to ask bolder questions, to imagine a universe far stranger than Einstein or any of us ever dreamed. Carl Sagan once said, "The universe is under no obligation to make sense to us." And that's the beauty of it. The cosmos doesn't owe us tidy answers or intuitive rules. It's our job to keep probing, testing, and revising, to embrace the chaos of the unexplained. So which of these radical ideas fires up your imagination? Is it the holographic universe where reality's just a projection, or the timeless quantum void where before and after lose all meaning? Drop your favorite in the comments, and if you're hungry for more mysteries, hit subscribe. The next revolution in physics could be just one experiment away.